Okay, good morning once again. Today morning we will just discuss the fifth unit of your syllabus, that is the stability of high-rise structures. I have already explained to you in the last week a quick brief review I have given. What is a stability analysis or why the stability of high-rise structure is important, and which are the factors to be considered when you do the design. Okay. During the design stage itself, the stability of the high-rise structure also has to be taken into consideration, because once the building is constructed and after that if you go for a stability check, anyway after the construction we have to do a stability check. Okay, stability check analysis has to be done once the building is completed. But during the construction stage itself or during the design stage or analysis stage, you need to consider the effect of the parameters which causes the stability of high-rise structures. So especially high-rise structures when you talk about, but in contrast to the low-rise structures, the stability aspect will not come much the consideration, because the low-rise structures maximum may be 2-story, 3-story building. It will not be that flexible. The flexibility of the structure will not be that high. Okay, once the structure becomes flexible, it is subjected to some sway due to some lateral loading, because the low-rise structures are not much affected by the lateral load. Okay, except earthquake. Earthquake.
Ma'am, can't see this. Ma'am,
Hello.
screen is not visible, ma'am.
No, I didn't share the screen. I didn't share the screen. Okay. I
Okay,
didn't share.
ma'am.
Okay. I'm just giving you an introduction. And the low-rise structures, when we are considered, the effect of lateral loading is, compared to the high-rise structures, it is less. Okay, but the earthquake loading effect will come even in case of a low-rise structures. But mainly, when a high-rise structure is concerned, the wind effect is more predominant than the earthquake. Okay, so earthquake effects are mainly for both low-rise as well as high-rise structures. Okay, because that doesn't depend upon the height of the building or the aspect ratio of the building. The concern for a high-rise structure is the wind load. Okay, wind load and effect of impact load. So all these are main concern for a high-rise structure. So the stability of high-rise structure is very important. So we will discuss in this particular unit, because the stability calculations are all empirical relations, because once you but all these relations are now incorporated in the software. So if you click the options that is available in the software, the stability check will be done by the software and you will be getting the result. But the formula that is fed in the software, for which are the effects that is taken into consideration for the analysis of the stability analysis. All these informations we will have a small introduction on this particular unit. Okay. So now I will share the screen. Now I'll just share the textbook only, because I have not prepared the PPT for that, because you need to can you see the screen now?
Yes, ma'am, visible.
Okay. So in the textbook, the 16th chapter deals about the stability of high-rise building. Okay, the stability of high-rise building. Just 1 second. So what is the necessity for checking the stability of a high-rise structures? So here we have seen that the increasing height and the greater structural efficiency of tall buildings have led to their having smaller reserves of stiffness, consequently the stability. Okay, so as the height increases, the stiffness starts reducing it. Okay, the stiffness will it will affect the stiffness. It will affect the stiffness. So that leads to the stability of the particular building. A check on the effects of this reduction in stability has become an important part of the building design process. Okay. So in considering the stability that of the structure as a whole, as well as that of an individual members that make up the building must be examined. So as a building is concerned, you can have a stability check for the entire structure as a whole, or you can check the individual members stability, independent members of the building like beams, columns. Stability of each element can also be examined. Okay, but the design for stability of individual columns is the same for high-rise building as far as low-rise structures, because a column is concerned, whether it is a high-rise building or a low-rise building, the column is the most vulnerable part of the building. So if that affects, the entire structure will collapse. So whether it is a high-rise building or a low-rise building, the individual design of stability of columns, the aspect is same. So in the design code, this part is already covered actually. This discussion on stability is therefore concerned with the whole structure or with whole stories of the structure rather than with the individual members. So this particular chapter deals with the stability of the whole structure as a whole. Okay, that means the entire structure as a shear wall structure or a rigid frame structure or a braced frame, infilled frame, outrigger. As a structure as a whole, how do we calculate the how do we find out the stability of the structure? Okay, or which are the factors that is affecting the stability of structure? So here I'll just read one or in between some sentences here. See here, in its overall behavior, a high-rise structure resembles a cantilever column of moderate slenderness ratio. It differs, however, from a typical structural column, which is essentially a flexural element. That means what? Because the previous chapter, previous units and all, I was going on telling the entire structure can be analyzed, or it will be considered, or it can be simulated as a single cantilever column. Okay, but that doesn't mean that that particular column is not the common column that we usually take it for a simple element or like that. Okay, so that even if it is a single column, a cantilever column, what is the main mode of that is it has a flexural behavior. It has a tendency to bend, or it has a tendency to sway. Okay, an independent structural column, if you take it, the nature of that particular column is to have a flexural deformation. It is a flexural element. You know that it's a flexural element. Okay, it has a capacity to bend. So we cannot consider, whenever we say that the entire structure is considered as a cantilever column, that doesn't mean it has the shear mode, the flexural mode, the combined mode. Everything has to be taken into consideration for that particular column. It is not a simple cantilever column as we usually do the analysis. Now analyze a column or analyze a beam. It is not like that. Okay, so by including the possibility of significant or even dominant shear flexibility, this shear flexibility component also has to be added in there. So after that, the potential modes of overall buckling include not only a flexural mode, a shear mode, and quite possibly a combination of both these modes. So that is what last chapter also I was explaining. It is like a cantilever column. Okay, so the predominant behavior is flexure. Okay, if it is a single cantilever column of an element, the main mode is a flexural mode. Okay, this is the flexural mode. But when we simulate the entire structure of a cantilever column, this particular mode alone cannot be taken into consideration, because the structure will have a shear mode. Okay, see, when it is loaded, it can have a shear mode of behavior also. It is possible, and most of the time, sometimes we consider for the analysis, we'll combine these two, flexure and shear, and we take a combined mode of buckling. Okay, so flexural buckling is not sufficient. Shear buckling also will be affecting in that structure, but most probably when we do the analysis, we combine these two and take it as a combined mode of buckling. Okay, that is what it is given here. Flexural buckling, shear buckling, combined flexural shear buckling. Okay, so that is what it is mentioned here. Then can you see the sentence where I am reading? The more serious stability consideration. Can you see the arrow mark when I am reading? Are you able to see that when I read? Can you see the arrow mark that is moving?
Yes, ma'am.
Okay. So the more serious stability consideration concerns the second order effects of gravity loading acting on transverse displacements caused by horizontal loading. This also last class I just explained you. What is the effect of, what is the meaning of S? This we will be discussing later. Okay. There is a second order effect. The first order effect is the just deflectional load. That is the first order analysis. When there is a cantilever, when it is, I'll just open a PPT also. It is 1 minute. So here, this is usually a cantilever. The first order analysis is nothing but we just find out the delta value. Okay, for a horizontal loading, this delta calculation is the main, that is the main parameter actually. That is the first order analysis, considering only the horizontal load, and find out what is the deflection and what is the moment that is causing due to the horizontal load. Okay, so that is known as the first order analysis. But what it says here is, see, the more serious stability consideration concerns the second order effects of gravity loading acting on transverse displacements caused by the horizontal loading or acting on initial vertical misalignments in the structure. Okay, I'll just show you the diagram. The vertical eccentricity of the gravity loading causes increases in the transverse displacements and in the member moments. In an extreme case, this is called P delta. This so-called P delta effect may be sufficient to initiate collapse. So the second order effect of the gravity loading is known as the P delta effect, that will cause that if it is not considered or if it is not taken into consideration, then this may lead to collapse of the structure. Okay. So usually, however, the P delta effects are either small or may be neglected or of only moderate magnitude, in which case they can be accommodated by small increases in the sizes of the members, or in the design of any high-rise building, it is prudent to assess whether the P delta effects may be significant. If so, that has to be taken into account for in the analysis and design. Okay. So in this particular chapter, the major discussion is on P delta effect. Did you understand last class when I explained what is the P delta effect? The last week I just explained you about the P delta effect, that I will come to you when it comes to the particular portion. Okay. So P delta effect is nothing but, so this is the first order analysis we do. What P delta effect says that when a particular structure, when it is acting, the gravity load is already there. Okay, and it is subjected to some horizontal loading is also there. So what will happen here? The structure will have a sway. So this axial, this gravity loading will be, this is a this is a deformed shape. Once it is deformed due to the horizontal loading, this gravity loading will be shifted. Okay, the axis will be shifted. So every time there will be a displacement is also there. Okay, so you have this P into this delta. Okay, this displacement, this P into this displacement, or this much deformation. Okay, so this deformation, this is the additional deformation coming at each story. Okay, here there is an additional displacement coming, that is due to the horizontal loading. So this P into Okay, this P into this delta. Okay, this delta will add together at each story level. Finally, it will come at the base of the structure. Okay, as a moment, it will act as a moment at the base of the structure. So this is usually it is insignificant. It is very small, but as the height increases, as the number of stories increases, then this the effect of the combined effect of the cumulative effect of this P delta effect will become more significant, and that is not considered along with the axial load and the other moment. This will lead to a collapse. This is what the P delta effect. Okay. Now we have another the overall buckling analysis of frames, approximate method. How do, because of the buckling. Okay, so buckling is one important parameter that is happening in a high-rise structures. So how the buckling will happen? Because of the gravity loading, and because in addition to the gravity loading, at the same time a horizontal load that comes. If that horizontal load is a heavier, much larger load, then this particular structure can have a buckling. A buckling can also be in the flexural mode. It can be in the mode of shear mode. Okay, so that is what methods for determination of overall buckling load. Because otherwise also you must have learned in your design analysis or your strength of materials. You must have learned how to calculate the crippling load or the buckling load of a column. Do you remember that in your UG classes? Either in strength of materials or mechanics of solids, you have learned the buckling load of a column, how to calculate the buckling, or we call it as a crippling load. Do you remember? Anybody remembers? What is the formula that is used to find out the buckling load? Anybody remembers? Or if I say it's a PCR, crippling load. Any idea? Just go back to your UG classes and see how it is, how you have.
Square A by L square.
Which one? Tell me.
Square A by L square.
Pi square EI by L square. Very good. Okay. It is pi square EI by L square. You know what is that formula called? It is the Euler's equation. Okay. Euler's buckling load. You have two buckling calculations you must have done. One is using Rankine's formula, other one using the Euler's equation. Okay. So as per the Euler's equation or the Euler's formula, we have the buckling load is equal to pi square EI by L square. What is that? L is the effective length. Okay. That L effective length depends upon the support condition. If it is a cantilever, then your L becomes 2L. Okay. If it is a hinged support, etc., the L one is both ends are hinged. Your L becomes L by 2. Okay, the effective length becomes L by 2. So similarly, you have found different end conditions. You must have learned. Okay, 2 pi square A by L square, pi square A by 4 pi square A by L square, etc., etc. You have learned depending upon the. So this is what this is for a normal column. So the every column will be subjected to some buckling. Okay, especially this buckling comes for a short column. Okay, for a slender column, the buckling is it will happen in slender column also. That buckling analysis is different. What you have learned is for a short column actually. Okay, so similarly, if it is for a slender column, the buckling effects are different. So that is known as the. So the what I wanted to tell is the entire structure we are making it as analogous to a column. Okay, so that column represents the whole structure. So the buckling analysis when we do, it represents the whole buckling of the entire structure. Okay. So here the methods for the determination of the overall buckling load are included because first it indicates an upper bound for the critical gravity load. Second, it allows an assessment of the relative vulnerability of the building to transverse buckling or torsional buckling. Okay. And third, it may be used in a structure for which an approximate P delta analysis is appropriate to evaluate an amplification factor for the displacements and moments. So that means usually first it is the effect of due to the gravity loading, then due to the transverse buckling is possible, or it may lead to a torsional buckling, or because of the P delta effect it will cause some displacements and moments. So this all will lead to the buckling of the entire structure. Okay, so that is given. I am not going to explain everything because you can go through this. Okay, please refer this chapter 16 and read and understand what exactly it is written over here. Okay, so in the shear mode, this mode of buckling occurs in moment resistant frames as a result of storage sway associated with the double bending of columns and girders. In the initial chapter 3, I have explained to you for a rigid frame what is the deflection mode of a rigid frame. I told you each beam and column will be subjected to a double curvature bending. Okay, so because of this bending, this shear mode of buckling can happen in a particular structure. Any effects of axial deformations, etc. So here there is a drift formula is given, how it is calculated, the drift and etc. All these entire derivations are given here. And finally, how to calculate the buckling load for the entire structure, that is also mentioned here. Finally, this is the combined effect. It is a combined effect. POCR represents the combined shear and flexure together. Okay. How do we calculate this? C represents the total moment of inertia of the columns by the height. G represents the sigma of moment of inertia of all the girders, all the beams together. Okay, so this is C and G. I think it is mentioned here. C. Ci is equal to sigma IC by H. Sigma IC represents the moment of inertia of all the columns together divided by the H. Okay, this is represented as C. Similarly, G is represented by sigma of Ig by L. Ig represents the moment of inertia of all the girders together by the length sigma is represented by G. Okay, so with that you can calculate what is the buckling load for this is the combined effect. Okay, and this is the shear mode. So all these things. So now clearly there is a flexural mode. How the calculations are done. I am not going to explain you all these things. It is, you just need to understand the buckling is mainly due to flexure, shear and combined mode of failures. Okay, so the combined mode is 1 by PCR is equal to 1 by flexure plus 1 by shear. Okay, so this is how you find out the crippling load for a rigid frame structure in the combined mode. Clear? So this is what. So similarly, the one that I have discussed now, it is only for a rigid frame alone, rigid frame. Now similarly, if it is for a wall frame interaction, wall means is the shear wall with the frame. Okay, shear wall with the rigid frame combination, how the buckling analysis has to be done. So the analytical methods, all these things are mentioned here. I am just leaving it, all these things. It is not required for you. It's not required in the sense you need to understand. These are all you cannot by heart any equations and all. Okay, so you just understand there's a big procedure how to calculate the buckling. See, the entire all these calculations have to be done, but manually we need not do all these things. Now it is available using the software. You can do that. Okay, there are coefficients are there. See, Sx, Xy, S0, so many instability coefficients are there. So from there you can calculate finally the critical gravity load for torsional buckling. Critical gravity load for the torsional buckling. Okay. So this is how we have to. This is sigma IW. Sigma IW means it represents the moment of inertia of all the walls together, shear wall together. Okay. So this is an example is also mentioned here. It is a combination of frame and wall together. Okay, stability of a wall frame structure, how to calculate the stability, the translation parameters, the torsional parameters, weight distribution parameter. Finally, you will be getting the overall buckling load. Okay. I hope it is you are able to understand. You are not able to understand the sense, not the problem. The concept behind it, why it is important. The buckling analysis is important. How to calculate the buckling load in the flexure mode, shear mode, as well as in the combined mode for all the structural systems that we have learned in the third module. We can find out what is the buckling load. In the case of, it can be a torsional buckling, it can be a transverse buckling, or it can be due to the gravity load buckling. Okay, are you able to understand? Did you get an idea? Please respond. Hello. Hello, are you able to hear me?
Yes, ma'am.
Yes.
Then why such a big delay in responding? Now, when I ask something, but I should know that whether I am audible or not, or just like that I am talking. What is your state of mind?
Ma'am, sometimes there may be a delay in audio, ma'am.
My voice is coming late?
Sometimes, ma'am, not every time.
Okay. Oh, now today Ergibe has joined? Okay.
Yes, ma'am.
Okay, very good. Okay, good morning and welcome, Ergibe.
Good morning, ma'am.
Morning. Are you here? Are you in Ethiopia, or did you come back to Chennai?
I'm in Ethiopia. I will come to Chennai next Thursday.
Okay. Good. Okay. Now, as I was mentioning here, the next one is the second order effects of the gravity loading. This is more important in stability analysis. So this already I have explained you what is a P delta effect. Okay. A first order computer analysis of a building structure for simultaneously applied gravity and horizontal loading results in deflection and forces that are a direct superposition of the results for the two types of loading considered separately. So that is the meaning of a first order analysis. First order analysis is what we are doing every time in your analysis. We are all your analysis subjects. What we are doing still now, it was only a first order analysis. In the sense, you calculate for the either for a gravity loading or for a lateral loading, you'll find out the deflection, you'll find out the forces. Whatever you are doing, either by using a slope deflection method or moment distribution method, or whatever analysis methods that you are following, every using that is known as the first order analysis of the structure. Just get the deflections and the forces by the direct application of the either a gravity load or a horizontal load, or we superimpose that. That's all. That is meaning of first order analysis. But for a high rise building, as I was mentioning, that is not sufficient. Okay. So any interaction between the effects of gravity loading and horizontal loading is not accounted for by this analysis. Okay. We will not consider the combined effect of this gravity and horizontal loading in the first order analysis. So in reality, when horizontal loading acts on a building and causes it to drift, the resulting eccentricity of the gravity loading from the axis of the walls and columns produces additional external moments to which the structure responds by drifting further. So this additional drift induces additional internal moments sufficient to equilibrate the gravity load moments. So this effect of the gravity loading P acting on the horizontal displacement delta is known as the P delta effect. Okay, I hope it is clear to you. So here there's a diagram that is given there. See, this is what I was explaining you. Okay. So the cantilever with the lateral and concentrated axial load. So when it is deforming, so this is a deformed shape of the cantilever. So your gravity load axis will be shifted here and this will becomes here. So you can see here. So at every story, this is the distributed gravity load. Okay, cantilever with the lateral and distributed axial loading. This axial loading will be distributed at each floor. So every time you can have a displacement is there. Okay, a horizontal displacement is there. So the addition, this P1 into delta plus P2 into delta plus, sorry, P into delta 1 plus P into delta 2 plus P into delta 3. So this, the entire moment will be finally added up and it will come to the accumulate at the bottom of the structure. Okay. So that is what. See, the second order P delta additional deflections and moments are small for typically high-rise structures with magnitude usually of less than 5% of the first order values. Okay, usually we don't consider the effect of P delta effect because this P delta magnitude, moment magnitude will be very small and it will be less than 5% of the first order values. But if the structure is exceptionally flexible, if they are exceptionally flexible, however, the additional forces might be sufficient to require consideration in the member's design, or the additional displacement might cause unacceptable total deflections that require the structure to be stiffened. Okay, so we need to, because the total deflection becomes very exceedingly large and it is otherwise if the P delta effect, if it is very minimum, we can adjust that in the analysis by adjusting the member sizes. Just increase the member sizes and we can adjust the effect of P delta effect. But if it is go beyond that, then that has to be taken into consideration. Okay. So in an extreme case of lateral flexibility combined with exceptionally heavy gravity loading, the additional forces from the P delta effect might cause the strength of some of the members to be exceeded with the possible consequences of collapse. Okay. So that is why this is it has to be taken into consideration. Or the additional P delta external moments may be exceed the internal moments that the structure is capable of mobilizing by drift, in which case the structure would collapse through the instability. Okay, so if the P delta effect is not considered effectively into consideration, the instability will be causing, that will lead to the collapse of the structure. Such failures would occur at gravity loads less than the critical overall buckling load predicted in the previous section. So for that only we are calculating the critical load, critical overall buckling load. If we calculate, if the gravity load is less than the critical loading, then such failures will happen. So your buckling load and the gravity load calculations combination you have to check. If that is a mismatch there, then it will lead to a failure. Okay. So this is the entire paragraphs you can read. Elaborately it is explained that I am not going to read everything about the translational buckling, torsional buckling, the P delta effect. Okay, how the torsional effects are coming into effect. All these are explained here. So for that, there is, how do we consider this P delta effect into our design? Okay, for that there's an amplification factor is mentioned here. An amplification factor is mentioned here because amplification factor, why it is amplification factor? Because it is an additional moment that is coming. P delta effect moment is an additional moment that is coming. So along with the first order effect, you have to take that also into consideration. So for that, an amplification factor is developed here. So it has been seen for a vertical cantilever displaced laterally by a uniformly distributed horizontal load, that the addition of a concentrated vertical load P at the free end of the cantilever increases the horizontal displacement by an amplification factor F. Okay. So that F is given as 1 by 1 minus P by PCR. Okay, what is PCR? In which PCR is the concentrated vertical load at the top to cause the buckling of the cantilever. This is the buckling load. This is the axial load. So 1 by 1 minus P by PCR becomes the amplification factor. So what will we do? So the final displacement delta in terms of the initial displacements, delta, that is delta star is equal to F into delta. This is how we take the second order effect of P delta effect into consideration in your analysis. The initial value of delta you can calculate using the first order analysis. that multiplied by the amplification factor will take care the P delta effect also into consideration. Is it clear? Is it understood?
Yes, ma'am.
So you have, similarly, it will affect the moment also. It will affect the moment. So there also you can apply the amplification factor, that with the moment you can multiply. So so the analysis of total drift and moments in the structure at the limit state under consideration would require. So these are the steps that is required. First, initially a first order analysis of the structure for the factored horizontal loading only. Second, the evaluation of amplification factor using the factored gravity loading and the critical buckling loading obtained from the approximate method that we have discussed previously. Now, increasing the drift and moments in the structure resulting from the horizontal loading, first order analysis by the amplification factor derived, then adding the results of 3 for horizontal loading to these forces in the structure determined for gravity loading. So, initial first order analysis, find out the amplification factor, find out the additional moments and displacement that has to be added along with the initial results, that is that you have done with the gravity loading. Okay. So this entire procedure has to be done if the P delta effect is taken into consideration. Okay. So that is what is mentioned. So similarly, you have another iterative P delta analysis and all. You can just leave that. Okay. So all this information is given there. Direct P delta analysis. So many equations are there. Empirical relations are there. You can use any one, and you can do that. Okay. Then simultaneous first order and P delta analysis combined simultaneously. How do you do it? Development of a second order matrix. All these things. See how the calculations. These are all. That is why in a structural analysis you must have learned the stiffness method of analysis. I don't know how many of you are remembering that flexibility method and stiffness method of analysis. So in that, the stiffness method of analysis is very important. That is the basis for a raw software analysis. Okay. You can see here how the. So this is what we have learned also in stiffness method, K into delta. The global stiffness matrix, the element stiffness matrix multiplied by the stiffness deflection will give you the displacements. Okay. So this is what you can use it. See. So many other equations are there. I'm just leaving all these things. Okay. Similarly, you have a translational torsional instability. This is also, it has also been taken into consideration. There will be an effect of translation. There will be an effect of torsional and combined effect. All this, these are all the second order effect. Okay, from the P delta analysis, these are all the derived parameters. Okay, translational, torsional, instability, etc. So how to calculate all these things? Okay, so you can see there are a lot of empirical relations are given here. Okay. Now the next most important instability or the stability effect is mainly due to the out of plumb effects. Out of plumb, that also last class I have explained you. Out of plumb means if there is a misalignment. If there is a misalignment between the axis of the column and the loading, okay, then there will be an out of plumb effect. When the walls or the columns are constructed out of plumb, the gravity loads acting on the vertical misalignment cause drift and moment P delta effect. That otherwise also you know, if the alignment is not proper, that will cause buckling, it will cause additional moment. Okay, so that is the meaning of out of plumb effect. Okay, out of plumb effect also how it has been taken in the worst German code of reinforced concrete. See, even in India, we don't have much information. Okay, Indian codes are not revised or equipped with the analysis of tall structures. Okay, so still for the analysis of tall structures, most of us even still we are following the Canadian code and the European code. Okay, the Indian standard has not, the code is under, because your IS wind code IS 1893 now it is revised. Not 1893, sorry, IS 875. IS 875, now it is revised, incorporating some effect of crosswind analysis, etc. But it is still not complete. For Indian condition, the codes are not that revised to taken all this into consideration. All this second order effect, all these things are not this thing. Then there is another one, the stiffness of members in stability calculation. What is the effect of stiffness? Okay. So I think this we can, I'll take in the next class. So what we have learned today is the what is that? Initially, what we started with the buckling analysis, overall buckling analysis, how to calculate the buckling load for a rigid frame or a rigid wall frame interaction, and the flexural mode, shear mode, combined mode. Then we went to the stability analysis, that is mainly due to the second order analysis of P delta effect, how to calculate the P delta effect into consideration with an amplification factor, then the out of plumb effects. So these are the three major stability criteria to be taken into consideration in a structure. Okay, so this is what we have learned today. With this, I will stop today's class, our class. I hope it is you are able to understand some of the concept behind this. Okay, so the time is over now. You have a class at 11, isn't it today?